So it's a pleasure to continue this series that we began this fall. And today we have two excellent young researchers to talk, and I'm very, very excited to see what they will talk about and have some interesting discussions. So the two speakers are Carlos Mastalli, I'm not sure if I'm pronouncing it correctly, and Majid Khadiv. And I hope that we made the right choice to combine those two speakers together and try to blend two different perspectives for solving the similar problems. And we will start with Carlos and then Majid, and then we'll have a discussion and questions. So each speaker will be talking for about 25 minutes, and I will try to start the discussion in the end, and then people can hop in and continue asking questions, or even the speakers themselves can ask questions one to another, so we can have a nice discussion at the end and hopefully have some nice outcome of this. So Carlos, the floor is yours. You can start presenting, and let's get the best out of this.
Okay. First of all, thank you for the invitation. As you might know, my name is Carlos Mastalli. I'm assistant professor at HERE-Watt. Also, I'm part of the National Robotarium. And in today's talk, I will talk about our efforts on building athletic intelligent Lego robots. So as this is a model-based optimization group, so this is about top-down approaches. So I like to call them top-down approaches, but we're talking about the same. And athletic intelligence is because we are trying to push the limit of what the hardware can do. So, okay. So, but first, let's discuss why we need to about motor intelligence. This is a brief introduction. So, there are many challenges remaining in model-based optimization, particularly, but I will say also in top-down approaches like deep reinforcement learning. So, one of the things is about designing accurate contact timings, complex contact locations to maximize efficiency in locomotion. As you can see, still humanoid robots are not able to walk as we do. And this is a quite complex problem to generate and to solve from many perspectives. Another thing is robots are still not quite safe to achieve what, I don't know, goats can do. And that requires a good understanding of what are the robot capabilities, but also what the environment is. To make decisions like the proper footstep location and to understand things like friction cone. And another thing is the versatility. So many robots are good doing locomotion, but less of them are just doing local manipulation. And this is a key enabling factor for deploying this robot to do actual useful tasks, such as, move a trolley from one place to another and pick up objects. And this requires to design a bunch of contact events, and the combinatorial complexity of this problem is hard, and this remains an unsolved problem. Here, because again, this is all about top-down approaches. So I like to call approaches that from first principles of optimization. The good thing, even if you are not in the field of model-based optimization, you might, I like to acknowledge that these approaches provide a structure, guarantees interpretability, which are useful. And this is what we can do actually with our robots. So because we can consider the full dynamics when we run an MPC, and also the limits of the robot, and the full kinematics, ANYmal is now able to transfer this kind of terrain where we reach, kinematics limits, and it's hard to balance because we need to move the body in different ways to increase balance. And also we can generate multiple jumps. This might look kind of easy, but here we're not changing the timings, and that requires an accurate tracking of angular momentum. And that there is when feedback MPC plays a role. And so you can see here that these are the feedback gains that we compute in real time for the trajectory. And this really improves the overall performance of the task. We have integrated this MPC, I mean, before describing the MPC and all the innovations we have done. So we have integrated this into a perceptive locomotion pipeline. Unfortunately, I'm not going to have time to explain all the bits, but basically, this boils down in the following architecture. We compute a height map from a terrain elevation algorithm, and then we extract a set of planes. These sets of planes are further reduced using kinematic feasibility and passes to a mid-integer algorithm that plans and selects a set of regions where we want to make a foothold. And also we use Rayberg heuristic to plan foothold location that are the targets, these footsteps, to our MPC. And the role of the MPC is to find a motion that ensures these footstep plans. So, and this is what we can do. So with our perceptive pipeline, so because the MPC with the full dynamics, either inverse or forward, and feedback gain produce a high accuracy tracking of the footstep, we can transfer, this is tiny stepping stones, and also our algorithm can deal with the, planning the footstep ahead. So these are some of the capabilities that we can do. Some of these videos are not publicly available yet, but we are in the process of, Thomas, which is here in the room, is in the process of submitting this paper. So what we can do is, climb up these boxes and these prove that the benefits of modeling the full dynamics, but also we have algorithms that avoid obstacles with the terrain, and then the feedback MPC plays an important role to track those trajectories. Another example, a glance of what you can see, from a point cloud, we extract these footstep regions, and we plan ahead, I think, eight steps ahead or 6, I don't remember. But these steps are the reference footstep position for the MPC. And you can see a target, a shadow robot that is the target or the terminal state of the robot computed by the MPC at that moment. So we model our MPC using hybrid dynamics, and this means that we predefine the timings of all the gate, and this is a kind of fair assumption when we talk about locomotion. So here, for example, in this diagram, we can see that we have different contact models depending on the phases, and also we have a preset math or impulse dynamics that between the phase 3 and 4, and we use this, and we have shown we have observed that this increases the convergence rates of our algorithm, and actually it's an important feature for converging as quick as possible for generating multiple jumps. This formulation boils down in the following equation. So we want to optimize a trajectory of the state and control, in our case for 1.2 seconds, subject to some dynamics. They can be contact, they can be forward or inverse dynamic, and impulses that are defined by the schedule of the motion. And also we minimize a cost that regularize the motion, and so and impose friction cone and footstep constraint. This formulation allows us to model or to execute different gaits, including jumping gait. And also it can be used to generate more complex maneuvers, such as this athletic behavior, where we only define the straight position and the landing place, and the rest of the behavior is obtained by the first principle of optimization. So as I mentioned before, one of the key aspects of our pipeline is the feedback MPC. And our feedback MPC is different to others because we are modeling the full dynamics. So from seminar work of Beware, we know that the full dynamics have some non-holonomics, and this brings an importance why we want to use feedback MPC, because it tracks the optimal policy. I will show you some results about this. In many of the papers out there, people use what we like to call this as a motion planning paradigm, where we have something like generates motion, in our case an MPC, but it could be a reinforcement learning policy, generating tasks, and we have an instantaneous controllers that track those tasks. Instead, if we think about motion and control as one single block, so what we can start to envision is what we like to call a motion control paradigm, where the MPC is not only generating trajectories, optimal trajectories incorporated in the state reference, as you can see, but also generating feed-forward torques and feedback gains. This build a local controller and actually have some impact as I mentioned before, in the execution. So here, what you can see, it's an MPC that have the same gate, the same parameters, and nothing has changed between these two experiments. Yet there's a difference in the behavior. So in the bottom, you see that there are changes in the pitch of the robot, and actually the MPC is commanding, and that's what the real MPC wants. It's commanding the changes of the body to increase the stability. But in the top, we see that the robot is walk quite straight. And this actually boils down in a bad tracking of the angular momentum, as we can see in the plot. And our state feedback controller can really track well the angular momentum, which is, again, important when we generate multiple jumps. This is related with the non-holonomy, and unfortunately, I don't have time to explain this in detail. But basically, what we can see is when we have a feedback MPC, we're tracking an optimal policy instead of an optimal trajectory. This leads for the increasement in the robustness, as we have observed in our experiment. Here you see that the animal, we push the animal, and there's the optimal policy have a trade-off between guaranteeing the task, which in this case, the footstep position in the place, and also the dynamic feasibility. And all this is done to encourage a good conversion rate. As I mentioned before and proved here, there are some improvement in the momentum tracking, but also in the swing foot tracking. We have observed with the whole body controller errors around 2 centimeters. We can be critical when we are moving over obstacles such as the climb stair or the pods that I showed. It really enables the generation of multiple jumps. Without the feedback policy, we cannot generate, for instance, this kind of jump, because there's a moment where the MPC starts to diverge so much, and the only option that we have is to adapt the timings, but we are not doing that. And as far as I understand, people from Boston Dynamics, they are adapting the timing. Also, if we have a solver that can handle, singularities, we build a policy that is, it doesn't suffer for kinematic singularities, or because we don't use any Jacobian. And I see this as a great point also as well. So, but all this is possible because we have we use DDP. But actually what we have, it makes some innovation in DDP, because DDP have some drawbacks, which I'm going to describe. Let me introduce briefly what is DDP. So DDP is an algorithm for computing, solving efficiently optimal problems, and consists in 2 main backward passes. The backward pass, it computes a certain direction. It tells us where to move, and the forward path, how long we should move in this direction. One of the good things of DDP is it exploits the problem structure, as we cannot do with NLP with sparse linear solvers. Basically means that we can exploit the temporal structure that is imposed by the dynamics or this Markovian process. But the main problem with DDP is the poor numerical behavior, which is associated with the single shooting nature of these problems. And this boils down because with single shooting approaches, it's well known that the nonlinearities cannot be distributed. And when we compute derivatives, those derivatives hold for a smaller neighbor, which leads to convergence rates that reach more iteration. Another important thing when you compare with NLPs is we run a nonlinear rollout typically in DDP, and there are some empirical evidence that this increases the convergence rate, at least for the case of DDP. But we come up with some innovation, what we call feasibility-driven DDP, and this is a start with the thesis that DDP is not really different to NLPs. And let's inspect a bit about NLPs. An NLP problem, when computing the third direction, has to solve a system of linear equations that come when we apply the Newton method to the KKT condition. This problem have more or less the form that we can see here. So we have to invert a large KKT matrix, which is typically for a quadruped around 40K times 40K. So it's a big matrix. and we exploit the structure using sparse solvers, linear sparse solvers. When we solve this problem, we compute delta X, delta U, which are the primal the direction for the primal variable, sorry, and we also compute this lambda plus, which is the net value of the dual variable. Instead, DDP, what it's doing, because it exploits the temporal structure, there are some connections that unfortunately I don't have time to explain here. So we can break this large, solving this large system of equation into a sequence of a smaller system of equation, as you can see in the equation in the bottom. That equation holds for it computes it solves the problem for a node, a running node. We can further condense this equation and get something that is quite similar, and we know about DDP, which is the last equation. But what I would like to notice here is when we think about multiple shooting formulations, so we need to consider the gaps, this F bar. So there are other terms that plays a role, and this is the blue term that we see here. This does not appear in DDP, but actually is related with the multiple shooting nature of our feasibility-driven DDP and typically the formulation that we use in NLP solvers. There's another thing. When we talk about the forward pass, as I mentioned before, NLPs, they run a line search. The objective here is to obtain the new guess of the bylaw, to keep iterating, and with some criteria that allow us to provide a descent direction and so on. But because we are talking about nonlinear problems, these third direction are computed using a linearization, and then we cannot apply typically the whole length. And that's why we need to find this step length alpha here. Instead, and we can have, depending on the alpha step, we can have infeasibility. Instead, DDP, what it does, it computes a policy and roll out in the nonlinear dynamics. This means that we have a feasible trajectory every time. Some people might associate this to goodness, but actually, numerically, this is bad because it doesn't increase the visiting of attraction to a good local minimal. What we do, because we have observed this, what we do is to have done here is to do a feasibility-driven rollout that is inspired by the numerical behaviors of multiple shooting. Basically, depending on the value of the alpha step, we can have a different infeasibilities in the dynamics, as you can see in the blue term. So when talking about formulations, we know that, typically people associate this with forward dynamics, but also there are inverse dynamics that we could use in robotics. Forward dynamics fits naturally into DDP or FDDP. And the reason is because with the forward dynamics, we can compute the acceleration of the system, the general acceleration, using algorithms such as ABA, and exploit the structure, the kinematic induced structure of our robots. But also we can apply constraint, any kind of constraint, and use the Gauss principle of least square to to have a composable optimization. And indeed, this is the idea that we pursue in Crocodile when we define non-holonomic constraints. But actually, this can extend to any kind of constraint, and there are some people doing that. Instead, in inverse dynamic formulation, what we have to do here is to incorporate the RNA equation into an equality constraint. And this is the gold term that you can see in the equation. This this equality constraint does not have the temporal structure typically that we have in DDP. But the one good news is we can decouple the integrator with the dynamics and distribute more these nonlinearities. This translates in increments in convergence range and be able to solve coarse optimization problems, as has been reported also in other papers. But when we include the contact, we also have to include other decision variables. And if you see, if you compare this with a forward dynamics, we have now extra decision variables for the general acceleration and contact forces, which makes a larger problem to solve and less efficient, as the algorithm complexity is related with the dimension of the system. So we have figured out ways to make this more efficient and to enable MPC with inverse dynamics. So if we look this equation is the equation of the inverse dynamic, and you see here that depends of the, for instance, the general saturation, joint torques, and forces. And this is the second vector that we see here. But if we assume that there's always a feasibility inverse dynamic, what it boils down to as an equation where we can condense the torques, so taus. And now we have a reduction in the number of decision variables in the system. Yet this, the decision variables are larger to the forward dynamics, as we can see in the diagram in the right. But looking into the resolution, if we go to the equations, the KKT equation from one node, and again, I don't have unfortunately time to explain where this equation comes, but you can see the papers. We now have this to incorporate the Jacobian of the equality constraint, which are the gold terms here. And if we condense in a similar way that DDP does, we get the following system. And now you see that now it's a larger system because we have to also compute, when we invert this, we have to also compute the Lagrangians of the equality constraint. But if we use a parameterization of this delta U, it boils down to a reduced system. Some people call this reduced Hessian in numerical optimization, because this is a smaller system to be solved. And now you can see that the Lagrangian disappear because we don't need to anymore to solve for that. But more importantly, this blue term here does not depend on the value function, which means when we compute the Riccati suite, we don't have to compute within the Riccati suite, and we can parallelize. If we parallelize this with a good enough of thread, basically this can be interpreted as reducing the decision variables. And actually, this the Riccati only depends on this U zeta, which is the part related with the null space of the control. And this is typically similar to the dimension of the forward dynamics. And this with improving the computation time. Also, I would like to talk about changing a bit of topic. I would like to talk about differentiable optimal control, which are some ideas that we are excited about it. So when I start this presentation, I talk about the goodness of optimal control or top-down approaches, because we have interpretability, structure, and this is nice. And a way that I think we can use for incorporating this is by first understanding that an optimal control or motion program, it generates a policy, and this policy can be parameterized by behavioral hybrid parameters like footstep placement, timings, contact, but also by any identification properties or parameters related with the robot. So whatever you can imagine here, it just has to follow a Markovian structure. And this policy, as we introduced before, is an main function that can be differentiable and is smooth on the typical condition that we use in optimal control. That means that we can compute the derivative, and that means that we can compute the derivative with respect to these theta parameters and have a composable optimization, or in other words, we can include other programs, we can include other layers and neural networks, whatever you think you want to include. But a good limiting factor here, it's scaling the computation of this analytical derivative to the cases that we want. And we have extended in our recent work, we have extended this to scale this for robotics problem, and we are working in an open source code. We apply this to the robot codesign problem, which is a larger problem. Here, what we have to do is to compute a motion given a task, let's say a trotting gait, and also we want to compute a robot design, which in our case is the dimension of the actuator, the distribution of the payload, the dimension of the trunk, and the dimension of the length of the robot. So because, as I said before, we can get the derivative of this optimization. Here is called the lower level, the motion planning. We can solve a larger problem by using by level optimization, where in an upper layer we can incorporate any kind of constraint, like constraints, inequality constraint, or in the bound, in the designs better. So, and this helps to compute, very quickly, design a robot very quickly. And you can see here. Here, this video is a bit accelerated, but this video runs for around one minute in a regular laptop, and you can see that giving a trotting gait, we are iteratively modifying the design of the robot, the dimensions of the front, the dimensions of the left, and the distribution of the payload to minimize some criteria, which in this case is the energy for executing this trotting gait. This can be used in different kind of motion. As you can see here, we have created this iterative tool where we play a motion and we optimize. So you see how the parameters that we are using here are changing by the optimization. And again, this is possible because we have a differentiable optimal control solver. And we can do this for different kind of terrain. So you can see here, we can randomize the terrain and build controllers, design robots very efficiently, again, in the order of 1 minute. As you might know, I'm very, very excited on open sourcing. A lot of these ideas take a lot of time to develop, and we like to contribute to the community. And we're happy with the current involvement. We have a lot of institutions using Crocodile, and feel free to join us. And some of these tools have been also used in different platforms, and some examples here are in quadrupeds, humanoids, and R, but also we have quadrotor, NPC, and so on. And most of the presentation has been possible because a great collaboration between teams in UK, France, and Spain, and these are some of them the main authors in this work. So before finishing, I would like to introduce the National Robotarium. This is a new exciting building initiative between the University of Edinburgh and Hero Watt here in Edinburgh, Scotland. And we are hiring people from different range, from academics to engineers. And yeah, feel to contact me if you're interested in this. This is all about my presentation, and I hope you have enjoyed.
Okay, yeah, so thanks a lot, Carlos, and I think we will move on to Majid, and please, the rest of the people, save your questions for the end, and we will have a nice discussion. Majid, okay. The floor is yours.
Thanks a lot, Konstantinos, and thanks a lot for inviting me. My name is Majid. I'm a research scientist at Max Planck Institute. And today I'm going to be talking about my research effort on the use of optimal control and machine learning control of basically robotic systems, especially rugged robots. I'm always fascinated and impressed by the type of basically agile locomotion behaviors human and animal can do in nature. And I believe while there is no immediate basically value in replicating this kind of behaviors on the robots, I think by doing this, basically trying to realize this kind of motion on the robots, we can move into direction of understanding better the main principles behind locomotion. And this is exactly what I try to do in my research. So the way I would like to, basically, I like to look at the control of robotic system is through the lens of optimal control, which was formalized by Richard Bellman. Basically, in general, we would like to bring a system from an initial state x0 to a final state xn. And at each state, like xk, there is a random transition to bring the system to the next state, xk plus 1. And there is a random cost associated with this transition. The main principle I use for my, basically for designing controller is the principle of optimality by Richard Bellman. And in plain words, it says that basically an optimal policy is such that independent of the initial decision and initial conditions, the remaining part of the control problem is optimal. So this is basically the principle of optimality or dynamic programming. And as it pointed out by Richard Bellman, here is the example he gives. Basically, if we consider only one basically point you would like to control in an environment, there are 3 position and velocity associated as the state of the system. Now, if you only consider 10 value for each of these states, we end up having something like 10 to 6 possible, values. And you can see how quickly, considering all the possibilities, end up being really intractable. Now consider we would like to apply plainly or naively this kind of principle to control of humanoid robot with 100 states, and where each state can move basically on a basically continuous manifold. So as it's pointed out by Dimitri Bertsekas, the exact solution of dynamic programming or principle of optimality in general is impossible. And this is what Richard Berman called curse of dimensionality. But interestingly, in most of the circumstances, there are some structure inside the problem that we know in advance. For instance, in robotics, we know the physics of the world, physics of the robot, we know some constraints, we know the geometry and so on. And we can use these kind of things, basically this kind of prior knowledge to design controllers. And also, we do not care really about the global optimality of our controller scheme. What we mostly care about is to find a suboptimal controller schemes that basically makes a balance between convenient implementation and adequate performance. And this is exactly what I try to do in my research. I try to find some controller schemes with some simplification and so on, based on the principle of optimality, such that we can really control robots. We can apply this controller to the real robots. So I will give you briefly, quickly, what I mean by control of this robot. So when we say we would like to control a humanoid robot or a legged robot, normally we would like to generate trajectories and track trajectories for the contact forces lambda, for the joint torques tau, and for the motion of the joints q. We have a system with something like n equal to 50 degrees of freedom or joints, and something like the number of contacts can vary between 0 to some defined value, basically. So we would like to minimize the cost functional phi over a course of time t. And this cost functional can be something like a tracking cost, some energy minimization, control effort minimization, and so on and so forth. And we have a terminal cost that helps us bring the system at the end of this time to a certain set. The main constraint of this problem is the equations of motion or the physics of the system, which is actually highly non-convex. The system is underactuated, which means that not all the joints of the robot are directly actuated by some motors or actuators. For instance, the base of the robot is floating in the environment, and it can only be indirectly controlled by the external contact forces. And finally, we have a hybrid system, which means that depending on the configuration of the robot with respect to the environment, the number of contact forces basically available can vary. So the structure of dynamics can change depending on the configuration. We have joint limits, which means each joint of the robot can move only in a certain limit, in certain area, basically. We have torque limits, so we cannot produce infinite torque by the motors. And most importantly, we have some constraint on the contact forces, which means basically most of the contacts we create between the robot and the environment is limited by the frictional unilaterality and frictional constraint. So this is the general problem we would like to solve. But in solving this problem holistically in general is not really tractable with the rates that we are interested in for replanning. So I think it's important to try to basically exploit all the structures inside the problem, and especially the basically different time scales, and try to find some kind of planning algorithm that plan, for instance, into the future and control with the short, for instance, horizon. So the first thing that comes to mind is the structure of the dynamics problem. Actually, it's well known now that the dynamics can be split to two parts: the unactuated part, which is basically the relationship between motion of the joints of the robot and the base of the robot and the contact forces, and the actuated part, which says how much torque we need to provide such that we can basically make a consistent motion, basically relationship between the motion of the joint and the contact forces. So if we assume at this point that we have enough torque in the joint, actually we can get rid of most of the equations of the system and also a large portion of the basically decision variables. Now we end up having the unactuated part of the dynamics as constraint. And interestingly, it can be shown that this can be exactly encoded by the centroidal momentum dynamics that you see in the bottom, which is the relationship between the contact forces lambda and the centroidal states, which are the center of mass, linear momentum, and angular momentum around center of mass. So now we have really a low dimensional dynamical system And this this set of dynamics, equations of dynamics, basically do not depend on the motion of the independent joints of the robot. So we only care about the center of mass and centroidal states. So at this point, we can actually start writing down and solving this optimal control problem, which is centroidal dynamics optimization problem, as you see. We would like to find trajectories for K, which is the concatenation of the center of mass velocity, and angular momentum around center of mass, and lambda, which are the contact forces. The main constraint of the problem are the centroidal momentum dynamics, where some parts of it are non-convex due to the cross product between center of mass and external forces. And the main inequality constraint, which is the most important constraint in the problem, are the contact force constraints. So this is, as I said, a non-convex optimization problem, but we can actually exploit the structure of the problem and write some customized solver to find the solution of this problem quickly. Once we solve this problem, what we can do is that we can write down a kinematic-only optimization problem, and we try to track the trajectories from the dynamic optimization problem while enforcing kinematic level constraint like joint limits. Also, at this point, if we want, we can also write down the constraints on the joint torques. And we can show that by going back and forth between these two optimization problems through a block coordinate descent type of approach, we can come to a consensus in terms of trajectories. Basically, we can have trajectories that satisfy the constraints on the forces on the left and constraints on the kinematics on the right. And normally in practice, really, we do not do many back and forth. Either one or two is exactly what we do in this back and forth optimization problem. Now, if someone provide us with some contact plan, which is basically the sequence of end effectors going to the contact, we can generate trajectories for the whole body, for the whole robot, and then we can pass it to an inverse dynamics, either constrained or unconstrained, in order to realize the trajectories on the robot. And here are the type of motion we can implement with this approach. On the left, you can see a combination of quasi-static and dynamic locomotion behaviors, multi-contact. And on the right, you can see a highly agile, basically motion. The robot can jump 5 times its standing height by using this basically kind of approach. Okay, it's good, but still with this approach, the dynamic optimization problem is still expensive, and we cannot really solve it with a very fast rate that we are interested in, something between 50 and 100. And also the other thing that I didn't mention here, for this kind of motion, I kept the delta t, or the timing of the contact switches, and p, the location of the contact fixed. While with this approach, we are able to basically adapt them, it gives rise to more computation and more local minima and so on. So for this motion, I just kept them constant. But the fact that it's the dynamic optimization or this dynamics is expensive to solve, actually, Avadesh and Pars has shown recently that using the basically alternating direction method of multiplier, or ADMM, and using the biconvex structure of the multiplication between center of mass and external forces lambda, we can actually solve this optimization problem through MPC with something like 50 hertz. So this is 50 hertz MPC on the real robot. So this is great. But still, we are not adapting step location and timings through this optimization problem. There are some heuristics out there you can use, for instance, Rybert heuristic to do that. But really, we would like to find a better way to also adapt the step location and time. Okay, let's see if we can do that looking at the whole dynamics and so on. So let's do a bit more simplification. Now, if we assume that the external contact forces, some of them, points towards center of mass, and the center of mass height only moves on a certain manifold. It doesn't need to be a fixed height. It can be any certain manifold. Actually, we can show that the non-convex part of the dynamics can be written down as a function of a stable dynamics and unstable dynamics of the center of mass. And if we only focus on the unstable part of the center of mass, actually, we can see that we can write down this dynamics as a linear or affine function of the contact location P of E and exponential of contact time, or gamma. So this is great because now we can basically write down a convex optimization problem and solve it very fast and adapt the step location and timing. And also, interestingly, it's possible to see that actually it's not necessary that we basically control the continuous part. By doing this assumption or enforcing this virtual constraint that you can see on the left, we can basically have we can go from a hybrid system to a switching system, and we can stabilize locomotion by only adapting step location and time. And this is great, because now we really simplified to the extent that we want. Now we can use this intuition and write down a very fast optimization problem to adapt step location and timing, both of them, by using the current measure the state of the system. Then we can find an optimal swing trajectory for the end effector that basically brings the system from the current state to the adapted step location and timing. And then we pass this trajectory to the whole body controller for track. Here's how we basically write down this step location timing adjustment program. So UT is the next step location, tau is the exponential of time that I talked about. And we defined this new variable that is really important. This is the distance between the divergent part of the center of mass dynamics at the end of a step and the step location. And we show that if we limit this value to a certain value, basically we can show that we can guarantee viability of the gate, which is basically the forward invariance of the gate, or basically the least conservative type of guarantee that guarantees that the system doesn't fall down, basically. And we have some constraints on the contact location, timing, and also the equations of dynamics that I showed. It's linear, and the last constraint basically is the viability constraint, the thing that I'd like to call. And these bounds actually for this system can be driven analytically. So this program guarantees that any viable state remains viable into the future, and I think this is an important property for this controller. So a couple of years ago, here is what I applied on a simulation environment. So this is Athena with the humanoid robot with passive ankle. And the robot is the controller is only adapting step location and timing. And you could see not only it can control the walking, but it can also recover from different types of disturbances. Also, one other interesting thing is that step timing adaptation is really important. Here we compared basically step location, our controller, which adapts both step location and timing, with an MPC controller that adapts only a step location. And we could see that actually we can gain a lot of robustness in terms of push recovery, as you could see in the figure. And some intuitions, basically, as I said, there is no need to control the center of mass at each control cycle. And with this kind of approaches, we can just adapt step location and timing to basically control the walking and do push recovery. I showed that actually we can guarantee viability by our optimization problem and bounds that we can put on the optimization problem. And finally, since we ended up having a very small optimization problem and it's only a QP, we can really solve it very fast. If you want, you can do it at 1 kilohertz. Well, it's not actually necessary, but you could do it at 1 kilohertz if you want. That's great. So the trajectory generation, so the program we solved gives us the next step location and time. And the simulation I showed, basically there, I generated the trajectories of the swing foot that connects the current state of the swing foot to the next step location using a heuristic polynomial. But actually the problem with this kind of approach is that toward the end of the gate, if the robot is pushed, the next step location and timing will be basically modified. However, polynomial-based trajectory optimization will fluctuate if you want to just fit current measurement to the next step. So here we did a heuristic that we just kept the adaptation. We didn't do any adaptation toward the end of the gate. And here you can see, for instance, in this figure, at the end of the gate, the robot was pushed, but since it could not adapt step location and timing, the trajectory diverged and the robot fell down. But recently, actually, we saw that for the trajectory generation of the swing foot, we can also write down another quadratic program. And the way we did it is that we considered the whole dynamics of the system, and then we mapped the whole dynamics to the swing foot, considering the contact constraint and the limits of the torque in the joint. And by doing that, we ended up having the dynamics of the system at the swing foot, And we could see that actually we can fit a very simple linear dynamics to this basically approximated with a very simple linear dynamics. And this helped us to write down this optimization problem. Now we have a two-level MPC. One adapts step location and timing, and the second one regenerate trajectories. And with this, you could see that now when the robot is pushed, the trajectories are tracked to some extent, and the robot could recover from this kind of disturbances. And we compared these two, and we showed that this two-level MPC approach actually benefited us a lot. And this was the thing that actually enabled us to implement a very robust walking on our biped robot. So this biped robot doesn't have any actuation in the joint, in the ankle joint. So it's a point feet biped with basically passive ankle. And here we are only adapting step location and timing to control the robot. And you can see we ended up having a very robust motion that can recover from external disturbances. The robot can walk on uneven terrain, on soft terrain. And also it can recover from a moving platform, which basically tries to replicate the slippery environments. Okay, this is great. Also, the same approach was used by my colleague Julian in New York University on a quadruped robot. So this shows that actually this algorithm is general enough that you could use for any legged robot with the different numbers of legs. And since you are adapting the step location and timing, actually you can have very robust locomotion behaviors, as you can see here. Also recently, we showed that it's possible that simply extend this approach to running motion. So the only thing we needed to do is that to relax the constant height basically assumption, and we find some proper manifold in the z direction for the center of mass, such that we can parameterize running as a function of that. And you could see that now we have the same controller, and we can do running on uneven terrain. And also, for instance, on the right, you can see the robot is running. It does push recovery. And also it can switch between running and walking seamlessly with the same algorithm without any change in the algorithm or in the controller. Okay, these are all nice, but we all know actually that this kind of things do not work on the first try. So normally what we do is that we start with our controller. We start changing some parameters of the controller, mostly the cost function weights, for instance, and see the behavior of the system. Then based on the behavior, we tweak some parameters, run it again. And then at the end, we hope that we can find a set of parameters that works on the system. So the question here, the next question for me is that how could we do this analytically? And here we proposed to use a sample efficient algorithm to do that. Here we use Bayesian optimization. And the idea is that we would like to perform just a very few number of experiments such that we can automatically basically tune the parameters here the cost weights of the MPC approach. So normally we have a cost function, something like this. We have several terms. Some terms are the performance terms, for instance, I don't know, velocity tracking, contact location tracking, or something like this. We have some regularization terms that try to push away the solutions from the boundary of constraints. And we have some invariance terms, basically, that tries to limit the motion of the system at the end of the horizon that we consider. And we have a set of constraints. So here we use Bayesian optimization to automatically basically find these weights of the cost function, alpha, beta, delta, and eta. And we would like to find these through a few real-world experiments. So here, for instance, we added different types of uncertainty to a simulation of a humanoid robot. We added, for instance, friction in the joint. We added a delay in the computation. We added all sorts of things that we can see in the real world. And also some external disturbances. And we let the Bayesian optimization to find the optimal parameters. The task here is that the robot steps in place. It goes forward with the desired velocity and then again steps in place, as you can see on the plot on the right. So the Bayesian optimization explores. Sometimes it could basically stabilize the system. Sometimes because of the pushes, the robot falls down. Sometimes it can manage to prevent fall, but it doesn't track the velocity we are interested in and so on. But here, for this, for instance, case, after only 13 queries, the algorithm was able to find basically a set of parameters of cost function actually that tracks the desired velocity very well, and the robot could recover from 50 different basically external disturbances that are sampled from a predefined set. So this way, basically, we can automatically tune the controller. Here, for instance, the weights of the cost function. And recently, through a collaboration I had with the Simon Fraser University, actually, we were able to perform this algorithm on an exoskeleton robot. So here, for the exoskeleton, also it's important that the robot could traverse different terrains. The robot, the controller can work for different type of basically users and so on, and also for different velocities. And here in this paper, for instance, and this work, we showed that actually through a few real-world experiments, we can basically adapt the controller to new terrain, to different users, and to basically different desired velocities. And for instance, for this simulation, I think it was after something like 18 query that the robot could find a controller that is stable on this surface, and at the same time, it can track the desired velocities. Okay, as a final portion of my talk, I would like to also basically scratch on the surface of the recent work we did. Basically, based on the thing I showed until now, we can control the robots in two different manners. The left one is a way that basically we try to simplify a bit the controller such that we can solve the optimization problem fast, and also we can find a convex resolution that gives us always a reliable solution. Or on the right, we basically try to solve the whole problem, but at the cost of being slower. So the next question for me is that how could we benefit from both of those worlds, or how could we have the best of both these worlds? Basically, we can have push recovery and being very robust, and at the same time we can generate a wide range of motion. And I think here what we can do is that we can try to learn the optimal feedback policy from the demonstration from either, I don't know, trajectory optimization or MPC. So here is an early work we did. We used trajectory optimization to generate demonstrations, and then we cache these solutions through a neural network, either using supervised learning if you have access to the actions and the states, or reinforcement learning if we only use state demonstrations. And then the important part is the next part, that we can start easily randomizing the height of the environment and initial condition of the robot. And using reinforcement learning at this stage, we can basically find a control policy that is robust to a certain basically distribution of the environment and initial conditions. And then we can deploy this on the robot without any further adaptation on the real hardware or any other randomization. Basically, the only randomization here is the contact height of the environment and initial condition of the basically system. And with this approach, actually, we were able to realize different types of motion that are actually difficult. And at the same time, you could see that the final policy is actually very robust. And it's a very lightweight policy, right? It's computationally super cheap. It's like a 2-layer neural network with few neurons that you can actually run it on a real, basically onboard computer that is very cheap. Okay, great. To wrap up, I showed that model-based approaches actually are very beneficial for generating nominal motions without any sample, without any reward shaping, and so on. And we can exploit, and actually to basically develop very efficient model-based approaches, it's essential to me that we should take the structure of the problem into account. Also, I showed that with the combination of a model-based approaches with Bayesian optimization here or any other approaches, we can have a fully automatic pipeline that can give us basically a working controller on the robot. And finally, I think reinforcement learning can help us to deal with type of uncertainties that is really difficult to take into account in the model-based approaches. For instance, contact height uncertainty is really difficult to deal with in a model-based approach like MPC. And I think combining RL and MPC can help us for this kind of thing. And with this, I would like to also thank all my collaborators and open the floor for the questions and discussions.
Great. Thanks a lot, Majid. That was a great talk. Really enjoyable. So I think I should start with a couple of questions to get the discussion going. And we are a bit over time, but that's okay. If both speakers and everybody can stay longer, we can continue the discussion. We don't want to keep anybody from their actual jobs, and so feel free to stay or not stay, whether you can do it or not. So I will start with a few questions. I think I will start with a question that applies to both speakers. And something that is always difficult when implementing model-predictive control on real robots is all the implementation, difficulties and all the fine-tuning that we need to do to actually make those nice algorithms work in real robots. So how do you usually deal with this, and what would be some rule of thumbs for people listening us today that we can help them to actually implement those? Especially the model-based approaches have a lot of small details here and there that are very, very important for the successful application.
Perhaps I should start. Can you hear me?
Yes, we can hear you.
Okay.
Yeah.
Well, I think all the algorithms have complexity. That includes reinforcement learning. You always have to tune something. In case of MPC, my experience is because we start to, there was a point where we started to develop this from scratch solvers, and to understand, what typically is seen as a black box for many roboticians. So understanding the behavior of the solver actually gives you a lot of insight how to tune. And actually, many of the cost functions, for instance, you have a range of values that you should try. I think it did not take, for example, the MPC that I showed. So it took me, I think, around a month tuning the. I have also experience developing a bunch of solutions before motion planning solutions. So I have, but it took me around a month to tune this with PyBullet, which is not quite fast. But after that month, so I practically those gains they work with ANYmal, they work with ANYmal C. So we have some experiment with ANYmal C that I did not show, but also with Solo, and they work also with a humanoid robot, and we are in the process to put this on a humanoid robot as well. So I particularly have not suffered so much about this aspect, but I took a lot of time. It took me a lot of time, around 2 years, to get the state where I want to implement something in MPC. So, yeah.
Yeah, I don't have so much to add to what Carlos said. I think it's absolutely difficult. So don't feel bad. It takes time to tune things, and the only thing that helps for me is intuition. So once you start working with the system, trying to tune things, then you understand, whether. It's really important to me in robotics that you know the limitations of your hardware. Once you start knowing this, then you can basically adapt your algorithm for that hardware. And this comes only with working on the system and spending time. There's no magic sauce from my side, at least, to do that.
So if I can add something, actually, I invest a lot of time in making the MPC to work with the right timing, communication, and actually I spent a lot of time on that when I was working the first time on MPC. But because I have worked a lot with the optimization aspect, so that was like a kind of done and check. But in the communication, we work with delay. So the MPC have some estimation of the delay, communication, things that are typically not well reported in papers, but yet very important.
Yeah, that's very, very good information, especially for the real-world aspect that, papers, we seem to forget to write about all these little details that are very, very important. So I have one more question for each of you, and then I'll let the people also ask their questions. So this is for Carlos, and One way, when I was reading your papers and looking at your presentation, listening to your presentation, one thing that struck to my mind is how can we combine all your nice approaches with learning? I mean, what is there left to be able to add and what we can gain from learning? For example, I remember Zustan and Nicolas learned the feasibility function so that they can improve the convergence of the solvers or something like this. Other people learn the dynamics model, in some way so that we can improve what we see from the real world. What would be your way of combining the things that you saw with learning that is also popular and also very effective in some cases?
So I guess you can get machine learning even in solvers, like hyper tuning of some, string parameters that are hard to tune. But and there are papers about this in numerical optimization. But my perspective, or at least my interest, falls in combining. So as I mentioned before, so you have differentiable optimal control. So think about these theta parameters where you can inject in the cost function, in the dynamics, and in the constraints. And now if you can do things like back propagation, or if we want to do forward network, like is becoming trending. So what we need is looking ways to do that. I can tell you about back propagation because I've been thinking about this for a long time, but there are ways of computing the derivative very efficiently. So when you solve an optimal control problem, you can add some extra computation to get those derivatives and potentially train systems with MPC. And why I think at least why I'm interested to train system with MPC is because the topics that I mentioned, it involves structure, it involves interpretability, guarantees, and we can also allocate or learn parameters that are associated. I mean, we can combine models. So if you want to combine to learn, the neutral Euler's equation, but you don't know extinction or some phenomena that are quite hard. So if you have a submarine and you have, wave. So there are many things that you might want to consider. And I think those can be integrated as parameters. And I don't think they should be modeled. Some of the processes are some of the phenomena are quite tough, and I don't think we should model, but actually get information from data. So again, you can combine these, but also you can do behavioral cloning if you learn cost functions. So you train a system that have different dynamics. It potentially can be a human being that with some motion, and you want a humanoid to track the motion. So what one task would be to just learn cost functions, and you can impose the theta parameters. Another thing is just combining. So adding increases safety. So if you put some theta parameters in, I don't know, friction cone or bounce, and depending on some condition, you can train a system that becomes more conservative or less conservative, given some training process. And you can actually do many things, and there are many exciting things to do. But in my point of view, and I think this might come from sort of last way of thinking from Gepetto team. So there are not the tools. So people is doing different from the learning because there are some great tools like PyTorch, and you can engineer a solution very, very quickly. But when we talk about MPC, it's not the same. Where we talk about rigid body dynamics, okay, there are some great tools, but come on, we are not at the level of deep reinforcement learning. And one of my motivation is to create those tools like differentiable ultimate control, and people can move beyond. And I think this requires a community, because that's literally impossible to do this alone, and that's why we are also putting a lot of effort in Crocodile.
Yes, I think I totally agree with you on this one, that we do require a community to reach the level of automation that deep learning and deep reinforcement learning have, so that we can move forward more faster. And I have one last question, and then I will let the rest of the people to jump in. So this is for Majid. I saw that you used Bayesian optimization. I'm a fan of Bayesian optimization as well. And there are a lot of nice work from my PhD supervisor, Jean-Baptiste Mouret, and others that are using evolutionary algorithms to produce nice priors for Bayesian optimization, so that we can more quickly adapt in the real world. And I guess you are more familiar with the work from LAS, where they're using this memory of motion that they create a lot of nice behavior simulation so that we can use them online to do things faster. So what are the views on, what are your views on this? How could we combine this with your approaches, or what you see as a perspective there?
Yeah, so I think it's to some extent it's very important, because we talked about tuning of these parameters and everything, and it's very difficult. We all know it's very difficult, and actually this is part of the automation for me, to be able to find an approach that automatically can find these basically set of parameters. And the main requirement for this, especially if we want to do it on the robot, which is the thing that we want to do, is that we need to be sample efficient. Basically, we cannot do an exhaustive set of experiments on the real robot. So that's why I think Bayesian optimization can help, or any other type of algorithms like that is sample efficient. But the thing is that, for instance, one of the problems of Bayesian optimization in general is that it doesn't really scale very well to the number of parameters we have. For instance, for a whole body MPC, we have something like, I don't know, 100 parameters or something that we want to basically find. Bayesian optimization really doesn't scale to 100 parameters. So we need to, what we did is that we basically put some other structure in the problem, reduce this to something like 20, between 10 to 20, and we could do it really with a few iterations. So I think the other approaches can be used, any other, like as you said, evolutionary algorithms or any other thing, but we should always keep in mind that the most important thing here is that we need to be sample efficient. So we cannot do, we have a limited budget that we would like to do experiments on the real robot. About the memory of motion, this is one way of that you can basically use previous experiments or experiences for basically making the new motions fast. And this is something that, we need to find a way, because when you do nonlinear MPC, especially if you go to whole body, I mean, there is no magic sauce again. You need warm start, or you need something that gives you the whole structure of the motion or something like that. And one way is memory of motion. I mean, there are many other ways, but one way is that. And I think this is one of the things that we need to move toward if we want to have MPC as a final controller that we have. So it's essential to think about this kind of problem that may not seem to be very important in the first glance. So what we want to do is that we want to find, optimization algorithm that converge fast and so on. Okay, these are all great, and we are doing it, and this is great, really. But the thing is that there are other things that are equally important, or also in the same level important. One of them is that, okay, how do you find these warm starts? Because you cannot always sit there and basically connect these trajectories together. Or how would you transfer this kind of thing or tune things for different types of motions? These are the things that are not, maybe they don't seem to be, that there are not many people working on them, but I think that they are very important. Because at the end, we want to have a fully autonomous pipeline, control pipeline, right? So we need to be thinking about all components of this picture, basically. So these are pretty much my thought on that. And I never have a proper solution for anything. So I don't know.
It's difficult to have a different solution there. That's true. Okay, so there are a couple of questions in the chat. Do the people asking them want to ask them in person, or should I ask them? It's Pierre Brice and Alessandro. You want to ask them yourselves, or I can ask them?
Well, thank you. I can ask it myself if you want. Thank you both for your excellent talks. My question is more for Carlos, because you have solved a lot of usual issues that have been hanging for a long time for the use of nonlinear MPC, for the control of legged robots. What's your opinion on the current status? Is everything important solved, or do you see what are the next important problems in the field of MPC for legged robots or more general robots? What's your opinion on that?
Well, I mean, if we talk about, there are different axes. One is differentiable MPC, but I mean, I already discussed a bit. When talk about MPC, I don't think the stories end, right? So, for example, we need solvers that can handle singularities. So we know in robotics we have kinematic singularities, and there's some great work done by Josh Klein in this aspect. Also, I do believe we can, at least what we are trying to do is to have a general solver that we can parallelize. So I remember when I start, the first time that I heard about DDP, people was complaining, oh, computational derivatives is the bottleneck. Then, tools like Pinocchio and others are pushing in this direction. But from my perspective as a, crocodile hat, I don't think derivatives are anymore, I don't see as a problem, but actually most of the computation goes into the backward path and including the forward path. So ways of parallelizing the backward and forward path is something that it's a research direction that has been pursuing. So we are working in a new solver that can, again, handle problems with rank deficiency matrices, singularities in, tasks like equality constraint tasks like the contacts. This is one direction. And the other direction, it's about content implicit MPC. I personally don't think that content implicit MPC can discover gaits. That might be debatable. I don't want to, enter in that debate, but my perspective is still content implicit. It's quite useful if we can manage to do this in real time, because we can have a controller that locally adapt the timing, the content. One way can be just looking into timing. I think this is what Patrick is doing, but and actually I'm not sure if we should only think about timings, but yeah, another way is looking into the content implicit aspect. Saying that, I don't think MPC can figure out content behaviors. And again, I think we should look into strategies that perhaps build some approximations, gradient, and that can be thing in, phrased into opposed into data reinforcement learning, where you don't use the approximation of the gradient and things like that. So yeah, another direction again is combining MPC with reinforcement learning. Not necessarily reinforcement learning, but sort of kind of deep learning. So another direction that we are very interested and exciting is centered by MPC. So now MPCs they use post-process information. For example, the state, you need to run a state estimator algorithm, or if you want to deal with some constraint with the terrain, so you need to post-process the pixels to get some high map, and then you get from some high map to some segment as we did, and then finally we use that information in the MPC. So there are a lot of steps that people is doing, and I envision MPC where you can, the inputs of the MPC is just for example pixels, and the way of doing this is by building a larger network. So because MPC is a graph, right? Neural networks is another graph. So building graphs where basically we can connect low sensory stimuli like pixels into high level actions, or a low level, I don't know if we should call it, but some actions that the MPC produce. I think there are many directions that we can work in.
Okay, great. Just as a reminder that we are running the best paper for the TC this year again. Patrick has put the information in the chat, but it's also available on our website. So yeah, let's continue. There is another question in the chat. So I think maybe I can ask the questions. So
well,
Alessandro,
okay. I don't know if you can see me, hear me. I can also ask you directly. Hi, Carlos. Hi, Majid. Hi, everyone. Yeah, thanks for the talk. Very nice, very interesting. Always to see a combination of optimization and on real robots are very, very, very challenging. Also, walking, jumping is fantastic. To see all these things happening on real system. Yeah, of course, you probably know that I'm also working on robot in dynamic interaction. I focus most on manipulation because I think that there's plenty of people just already doing locomotion. And so, but in any case, the problems are similar. So we are interested in having robots grabbing object, pushing object, multiple impacts. And of course, MPC is very interesting, but I wanted to hear your experience on generating this motion that where maybe indeed the task is touching, with all the legs at the same time, but then in execution, this is not really happening. And maybe you have high gains, so I can imagine that there will be some issue there. And I don't know how you actually deal with those at the moment. And also both from computational point of view in the MPC, but also then on executing those things on the real robots. I would really love to hear your experience there.
So I can go for this. So the issues are all there. I mean, when you do MPC, normally you have actually certain different time scales, and especially when it goes to a context switch, it becomes very difficult. And normally, in controller, we do not take explicitly into account the effect of impact. We implicitly always try to mitigate the effect of impact. This is at least what we do. Basically, we are not trying to exploit this kind of impact. And this is mainly due to the fact that in the MPC, we are replanning on a certain time. And impact is a very fast dynamics that normally happens in between of these planning times. So what we do normally is that we resort to some kind of approaches that we go around impact or context switch that is unexpected. So it's, to me, because it's very difficult to take it into account, as it's a very fast dynamics in the context switch. What we do normally is that we go around it, doing something like that. And I think I cannot find any immediate remedy for this, for using model-based approaches like MPC, because normally we have hierarchies, and basically if the context switch happens, we need to go back to all hierarchies and try to adapt all of them based on that. And this makes it very difficult. At this point, to me, the thing that works the best for this kind of situation is that we try to basically learn one policy while we could use these model-based approaches to generate proper sample. And this is, for instance, the last work we did, and it worked really well with the contact uncertainty, which is one of the most important, basically, problems we have there. So basically, we try to find one policy that basically caches the solution of the system that have contact with the environment at different times. And this is basically what we did. So I think, again, the main challenge for these systems with MPC is the discrepancy in the contact timing. And this is what makes it very difficult in general. And the thing that I found it working, I mean, I personally couldn't find any way to take that into account, contact timing uncertainty and so on, in the design of MPC controller. And I think it's very important. But I think learning was made our life easier, and we could basically learn a controller that is robust with all these uncertainties. So yeah, this is my take on this. And I think if you don't have contact, the delay in the MPC computation and everything, I don't think it's really a problem. When it becomes really a problem when you have a context switch, and that's the most difficult problem that, again, I don't have any answer for it for the MPC side. So I don't know, Carlos, if you want to complete or if you want to add something.
Yeah. So from our perspective, so I will say that you need a contact implicit or adapting the timings because you don't know exactly when it's going to happen, this contact and impulse. But with the feedback MPC that I present, we have such kind of good tracking that the delays when you expect to do the contact are not really important. So if you see these multiple jumps, so we don't change the timings in any of this motion. And actually, so if you run, as I was saying, if you run a robotic controller, because the tracking issues that we have, while you can tune the policy, because there's the concept of optimal trajectory and the concept of optimal policy in my mind. So when you have tuned these tasks, you are basically putting your policy. So that's part of the explanation why the robotic controller cannot run that well. And we spent around 2 or 3 years to get this whole body controller. That is, I will claim this is a whole body controller state of the art. So it was properly benchmarked. So yeah, again, these small delays, they were not a kind of issue for us, but because we have a feedback controller. But obviously, if you the floor move, let's imagine that your perception system is telling you that the floor is going to be 10 centimeters high. It could be possible that the MPC deals with that, and that's impressive. But it's very unlikely that we'll make another jump. So let me tell you a story. These jumping gaits. So all the experiments I run with onboard state estimation, with the exception of the jumps, because none of the state estimator. I'm talking about the ANYmal state estimator. I will say it's a very good state estimator. But yet when you are jumping in a fly phase, you can get in around 300 or 400 milliseconds, you can get an error of 10, 15 centimeters only on height. So think about that, we are just jumping in place. Also, there are errors in other direction, but so can you imagine how a controller can deal with that? Well, the MPC surprisingly deal with that, but just for one jump. The next was trying to do a jump that basically unstable jump and leads to a fall. And again, with a whole body controller, when you have backtracking, so this perhaps doesn't happen in the first jump. Perhaps you can do a second jump, even perhaps a third jump, but I don't think a living our experiment beyond 3 jumps, it was impossible. So I tried up to 15 jumps, and I didn't try so much because my line manager told me, Carlos, please stop running jumping experiment. But I believe it can do a lot of jumps, the system. Again, so yeah, dealing with contact implicit, I think it's something we have to do, but we are not really doing, and still MPC can handle a bit some of the delays that could happen. But yeah, that's not the ideal case.
If I can squeeze in the discussion here, there is some interesting work by Marco Utesrab in this regard, that they learn in simulation a model that learns how to avoid and how to adapt the MPC reference signal when the elevation map is not correct. For example, they were getting very bad elevation maps for grass stuff and these kind of things, and then they were able to correct it. So maybe that's a region where we can combine learning with MPC and actually get the best of both worlds, because some things are just easier to do with learning and some things are much easier to do with, much better to do with MPC, and we get all the nice details.
Guys, if I can bring my own experience, I have a solution for this issue that worked in practice. And the idea was to, whenever you get the contact in a wrong moment, let's say a premature contact or a delayed contact, you immediately trigger the change of state in your controller. But you could actually fast forward or rewind the contact scheduler that generate the contact schedule for the MPC. And this way you reconciliate the real contact condition with the planned expected planned contact condition. And this was very important, for example, in our quadruped robot walk, in case of this premature or delayed touchdown. So we were, let's say the contact was expected to, in some moment, didn't arrive, and the MPC optimization without this feature of delaying the contact schedule would inject would dictate a different trajectory, expecting the contact would happen, or the other way around. So it was important to do in this way, but is a solution. It could be addressed in a more formal way for sure. But we wrote this in our paper IEEE Access in 2021. If you want to have a look, but certainly is an important issue for the MPC optimizations.
Yeah, thank you, everyone. Yeah, to be continued then.
Okay, so I don't know, are there any other questions? If someone wants to ask something, or there is something else to discuss. Majid, Carlos, I don't know if you want to ask each other a question or say some final words, and I think we're way over time, and it's about time to wrap it up.
Yeah, we're way over time, so I'm not going to ask this question. I'm just going to note that for everyone that was talking about parallel things, that's sort of my jam. I love trying to accelerate things in parallel. So I would love to talk, potentially Carlos offline about that kind of stuff for Majid or anybody. But I'm not going to ask the question because it's already 11.
Yeah, there is also one more question in the chat that I missed. And I guess this is for Carlos, a quick one, and then we wrap it up. So they say that FTDP takes a nonlinear rollout scheme, and you mentioned that this scheme has larger region of attraction. Is this a conclusion made based on some comparative studies? Did you compare nonlinear rollout with linear rollout and hybrid rollout?
So we haven't compared. There's, I think, two questions here, or two answers at least. So we haven't compared nonlinear rollout with linear rollout. But there are some papers that have done this, and actually quite old papers, I think around the 90s, where they show a graded convergence rate. So basically they have a DDP algorithm, and then they use a problem, so with dynamics, and then they have the same thing with NLP, and they show that the convergence rate increases when you have nonlinearities in the cost, but also when you have nonlinearities in the dynamics, and when you have both, actually the convergence rate is faster. So there's not, as far as I know, rigorous evaluation of that, but this empirical evaluation, which I haven't done, I still was a teenager, but I will say it increases the convergence rate, and I thought it would be nice to have a paper that shows this in theory. Then the other question is about not linear against linear, but I will say feasible nonlinear and infeasible nonlinear. So which is the FTDP question. So we have observed, and we don't have perhaps although that we have a lot of problems that we have tried this, perhaps it still is not enough. But in all the problems that we have tried, without any exception, and also in forward and inverse dynamics formulation, we have seen that the FTD, that running as simulation that is infeasible increases the convergence. For example, you might see this Atlas motion that I shared. We can compute both with inverse dynamics and forward dynamics, but only if we use the feasibility-driven approach, because we have injected the feasibility-driven approach in our, we can inject in any kind of solver that handle in a number of different constraints, not only the dynamics. And we have developed the two versions when we developed this. Unfortunately, the publicly available in Crocodile is only the feasibility, because it always worked well. But yeah, it was not possible, again, to compute those problems. The algorithm was simply diverging. It was not getting to any reasonable solution. And the same happened with jumps. And we report this in Crocodile 2 years ago, I think. And you can see a video where we can generate a jump if we don't use this FDD. But the thing, it's the same with inverse dynamics. Yeah. And this is because I guess this might be explained easily by when you do this infeasibility research, you have some guarantees, because in numerical optimization, people have done this for decades, and there are a bunch of papers that show you guarantees. But in case of DDP, it's an empirical way of doing things, and in my opinion, it doesn't have any proof of goodness. So that's why we try to go back to NLPs where everything is clear and to mimic this behavior.
Okay, great. I think we should wrap it up. Let's thank again Carlos and Majid. I think it went very well. I really liked the discussion part. It took a lot of time, but I think that's the most important part of this seminar, because we are able to discuss open challenges and exchange ideas, which we don't always get the chance. So thanks again, and stay tuned.